Okay, good afternoon, everyone. So let's get started. So today we are very honored to have our speaker, Dr. Gerold Schropfer, to visit us from Lam Research. So actually, Dr. Schropfer is now a senior director at Coventor, which I just learned used to be a MIT spin-off and then was acquired by Lam Research some time ago. So actually, our speaker will tell us a little bit about history momentarily. So right now, Gerold is based in Europe, in Paris, actually. So he has been working on MEMS and semiconductor activities. So before the current position, our speaker has experience in MEMS and semiconductor design, process development, etc., as well as magnetic sensors research. So our speaker has a degree in engineering science and also physics. So without further ado, let's welcome our speaker. Please.
Thank you for the kind introduction, and thank you, first of all, for giving the occasion for presenting here in front of you. It's a really honor to be here and to share some of my experience. The title is a bit long and awkward. I was trying to find a compromise between sharing some experience on what we do today, working with leading MEMS companies, but still also trying to give a bit more background on the history, and also stating right understanding about MEMS. It's all about understanding how little tiny things work, and simulation tools is one of the way that can help with this, and this is not only relevant for industry. So the outline I propose is to give an introduction. There are actually three introductions to Coventor, to Lam Research, and also computational products. That is the division we belong now. Talk then about the challenges of MEMS and what we as Coventor proposed in terms of a design flow and digital qualification to handle these challenges. And then give a number of case studies just to give examples on how design flows today are used, and conclude with a short outlook. MEMS came a long way, right? So my experience started with right on the automotive sector. After my PhD, I was doing tire pressure sensors and accelerometers for airbags. So there was safety, the requirement, and medical devices. This now involved, actually, especially if I take tire pressure sensors, they save lives today, still about 500-600 a year in US only, but they contribute also to the sustainability, to environmental, and by reducing gas consumption. So MEMS has an important role in society, and over the automotive industry, we moved into smartphones where you have gyroscopes, microphones. Each of you may not be aware of it, but you're a daily MEMS user, right, with your smartphone and other devices. And now we go into applications. Metaverse is one of the buzzwords, right, where there's a number of new applications in augmented reality, virtual reality, using actuators, using audio devices, using inertial sensors are important. Autonomous driving is one of the key drivers to drive technology and design. So there's a bright future for MEMS devices with lots of different applications. Huh? So talking a bit about history, what is Coventor? So we come out from MIT, and that's why it's really an honor for me to be here, because we are a spin-off from MIT. The first code that was written here by John Gilbert, who was a postdoc under Steve Centuria, who is among the audience, and I believe you will tell us afterwards a little bit more about the history. So this is the first code, basically coupling electrostatic simulation with mechanical simulation that didn't exist at that time. And that was the technology piece that helped to found Coventer now 25 years back. And since then, we focused on basically helping the MEMS industry to develop their devices in a more automated way to get new products to the market. About 10 years ago, we added a semiconductor solution, meaning semiconductor process simulation to our portfolio. We call this product Simulator 3D. And then 5 years ago, we have been acquired by Lam Research. So it's a large equipment company. Most of you may know the company, but it's something different because MEMS are different. A software company is integrated into a system company. And let me tell a few words about Lam Research. So it's one of the largest semiconductor equipment company, now serving 40 years, basically all chips that we use today, advanced logic, advanced memories, specialty technology like MEMS, they have been fabricated in some way with Lam equipment. So it's a company that is providing the standard areas of processing at deposition. Lam is very good in etch. That's where the company started. The founder, David Lam, he was one of the inventor of plasma etch. We have also strip and clean, and then a number of growing service and support products. I didn't want to show a lot of financial numbers, but the company is a big it's a big player in this industry, and we are investing in our future. So we continue to work with universities. We have a number of research and academic programs and university programs where we collaborate actively with universities around the globe. And I give you just this number, 1.5 billion that Lam is invested 2001 into research and development, so quite a large number. And we have facilities also in-house in Fremont, where the company is headquartered, at the Rick Gotcho lab, as well as a new tech center in Korea. And obviously, as it is a manufacturing company, there are manufacturing facilities around the world, based in US, in Oregon, in California, but also in Asia. So it's not all about hardware, right? One of the reasons why Lam acquired Coventer is to enforce the modeling part, the virtual simulation, virtual processing part, where we add value. There's also predictive analysis and different types of support that certainly get over the last 2-3 years with the COVID pandemic. More important, which is now an industrial standard to virtually support customers worldwide. So now about computational products. So this is the division that I work for, and I have also here a colleague with me, Matt Cameron, who actually came out with his PhD from MIT. So we as Coventer are basically a part of this division that was born out of the merger between the companies. So we keep our Coventer name, we keep our entity, and we keep developing our external products, which is Coventer MP for MEMS design and simulation, and Simulator 3D for semiconductor process modeling. But in addition, we have a number of internal products that we develop, which are exclusively for internal usage on virtual process simulation and lab business systems. And independent if it's internal or external, we collaborate with our customers, with our MEMS and semiconductor external customers, but also a lot with the Lam research engineering community, which obviously has a large and deep know-how on process simulation. And underpinning this, we use a number of competences, data science, machine learning, that are shared between this group. So I wanted to give one slide overview of our simulator 3D platform. The idea is really to virtualize the complete manufacturing flow. We describe the process flow as it happens in the fab. Behind each technology step, there is a behavior modeling step. So you have a run card based on process steps and attached simulation steps for each of them. And then the other part that you use is the design data, which can be GTS or more elaborated data like OPC, contour plots. And these are the two parts, the process description with modeling steps and the design data that you combine in a virtual fab modeling engine to simulate, I would say, any kind of semiconductor type of devices. It's a tool that is now very well established in the advanced semiconductor, advanced logic, advanced memory market, but we see it also used in the specialty technology. That's the market we call, for example, for MEMS or for power devices. And its application are about pathfinding, starting when you start basically a new technology, figuring out the process integration scheme, doing larger decisions, big branch decisions like we call it, or process assumptions. But you use it also for detecting defects, analyzing defects, things like 3D failure checks, structure getting more and more complex, and it's really the structural complexity of the new generation of semiconductor processes that make this tool necessary. And we also do support the manufacturing side by estimating yield, helping with ramp up, playing between design and process. So what is the variation on the process? How it affects the design and vice versa? And process window studies and cross-wafer uniformities. Remaining of the talk, I would like to talk about, let's say, the product line my team is working on. We call it now Coventor MP. MP stands for MEMS platform or multi-physics. And it's a platform that is composed out of Coventorware. That was the original product of the company. We called it in earlier days MEMCAT, right? That was the first name, and then the name changed to Coventorware. It's a suite of different field solvers, finite element types of field solvers. And over the last, let's say, 10 years, we developed a complementary suite, which we call MEMS Plus, which is more compact modeling. So you can do device modeling, but we also use this platform to do combined device and system simulation. Similar like simulator, we use the layout data, design data as input, and have then a process and material description to combine those and build a model. And our focus is, because we want to be different than other standard tools, so we focus on having models that are fast enough for prototyping, but also system integration. Accuracy is important. You need to match reality to be at a level that the users expects, and overall also automating the design process, going from the process to device to system is something that we implemented. Talking about a few applications, so we don't want to do everything. We focus what I call the traditional MEMS market, so MEMS for electromechanical systems. So if things are moving, this is usually devices we can well handle. So traditionally, we are very good in gyroscope and accelerometers. Now, especially gyroscopes, they get more and more complex in geometry. Microphones, the platform is used by the major companies developing microphones, also actuators like switches or mirrors, or more, let's say, maybe research devices like energy harvesters or other type of mechanically moving structures. So this is the type of devices we cover. We don't cover, for example, microfluidics. This is something we decided to leave to others. Okay, after the first introduction, let me talk about some of the challenges we see. And I start with a slide that I made maybe 15 years ago, maybe older. But while the industry continued to evolve, while we continue to develop our products, most of these challenges are still true today. So MEMS are inherently multi-physics, and this is coupled. So you have the mechanics coupled with electrostatics. You have damping mechanisms associated with it. Sometimes you have other physics like piezoelectrics. But you need to consider all these physics in a coupled way, which is non-trivial. And MEMS are inherently different from IC because they are 3D structures, and these 3D structures can be simple beams, can be simple membranes. But if you look on the advanced devices, like a gyroscope, it's getting more and more complex. So it's like the, British would say the Victorian mechanics on a micro scale. So it's interesting geometries, but complex to handle. And then whatever is the MEMS device, a MEMS device is never by its own. So you need to have an electronics, and the electronics need to talk to the MEMS device for readout, for actuation. So what is the approach now to co-design the system? You have a multi-physics system, and you have the electronics where there is a whole world of very well-established methodologies. So you need to bring these together. And then once MEMS and electronics are done, you need to put it in a package, and you will see that the package, there's a different material, there are temperatures outside, so this package will affect the mechanical multiphysics behavior of your device. So MEMS are usually a good temperature sensor, and you need to try to avoid that this packaging is disturbing your function of your device. Overall, there is still not a really standard MEMS process like you have in CMOS, where you have dedicated PDKs and you can go and select the process and you don't need really to understand. So usually the process is still a part of the design variable that you need to consider, even though standardization has taken place. But there's always a small part you need to deal with. So this is a challenge, and also the variability of manufacturing. So this is now more, let's say, a standard for companies to take into account, but you need to take into account the tolerances of the manufacturing process. And it's not only the geometry, it's also the material properties that vary. And depending what the materials you use, there are mechanical devices. So crystal silicon is quite well characterized. You can take literature values. For other types of metals, for example, if you use them, they may only exist in the fab you have, so you need to characterize because it's a homegrown material. And then over time, performance will degrade, so you need to take this also into account, and that's another whole range of reliability-related topics which is of interest. So how can you tackle these challenges? You can do something which is very, very simple, but that might or might not fulfill your need. Usually not, because it's too simple. You can do back of the envelope calculations, which is always good to do, right? But usually these are simplified, and there are lots of assumptions that might be simplified. So it gives you an idea, but it doesn't give you the high accuracy. And then a third approach is you don't simulate too much. You just have a large set of different structures that you just try out. Hopefully some of it will work. And this is actually an experimental approach that is still, I think, used a lot of in MEMS. But then the fourth approach that obviously as a software company we would like to promote is having a standard or a well-established methodology how you design and simulate your devices, having a predictive, as much as predictive simulation tool to allow first round success in silicon, which is more or less the standard in IC. In MEMS, it takes usually still a lot of iterations. So today, MEMS products take still 4-5 years to develop if it's established company, established technology. Last week, Google announced their cross-connect, an optical cross-connect for switches in the server room. So for those who worked in MEMS 20 years ago, there were lots of companies doing these cross-connects. It's a mirror array. And all these companies more or less disappeared. There were small ones, there were large ones. So now, 20 years later, Google comes up with a product that is now used in Google server rooms. It's officially announced. It took them almost 10 years to develop. So there's still room to improvement, right? And so I honor also Steve Centurio with this slide. So this is from a very good book this book we recommend, to every new hires we get. It's a book of Steven Centurio. The engineer gets this on his table to read if he hasn't done so. But this is a slide. It is an overview on the different models. I like to use it because it's still true today, right? As a MEMS designer, you just can't ignore the process. You need to know how the device is manufactured if you want to do your design. And you can't just focus on the physics and on the device level. You also need to look into the system. Maybe it's your colleague that is designing your systems, but you need to interact with this colleague to make the complete simulation or development flow. So right, you can start from the process and you can end up into the system, which is here called verification. You can also call it bottom-up design. This is the procedure or the flow that you find mostly implemented in our tools and in other, let's say, methodologies. Or you can go from simulation. You start with the system level and you end up with the definition of your physical parameters. Huh? But in a way, this is the flow that you find in our tool and in other methodologies as well. So now I already, I think, touched on this, but there are now different phases, conceptual, detailed, optimization, verification phases during your development, and there are different levels. There's the device level, there's the system IC level, and there's also the package design. And in a conventional flow, you use analytical modeling, which is good enough, but then if you want to increase accuracy, you use finite element analysis for detailed design and optimization. So one of the challenges is that this finite element analysis is not really compatible with an IC or system design flow, huh? Because it's multi-physics. You can couple it, but it usually takes time, and in some cases, if the complexity is large enough, it's even not possible at all. Huh? And so there's no automation to the MEMS and IC world. It's a wall separating those. And then if you go to package design, again, it's finite element analysis, but how you link this back then to the IC design or to your MEMS device design. So it's an ad hoc method. And these areas are really not connected. So that's what we tried to change over the last 20 years, right? So we introduced a method called compact modeling. There are other ways how to characterize it, and I will explain later on what this exactly is. And this allows you to have a multi-physics design on a conceptual and also detailed level, but in a fast way, right? Because you give up some degree of freedoms and you gain simulation speed. And by doing this, you are able to have a model that can be shared in not only device, but also in the system level. So you can use this in simulators like I see simulators from Cadence, Virtuoso, or MATLAB Simulink. And this is in an automated way. And then also you can include a package design, which is finite finite element based, for example, deformation of the package. So these are larger structures, but you can now feed back this deformation to the MEMS device to incorporate the temperature-induced deformation of packaging, affecting the tiny details of your MEMS device. And you always need traditional finite element analysis for certain verification, for certain specific aspects of this flow. So for example, from MIT, there's FastCap, electrostatic solver, which is still used in industry for very accurate, precise simulations. Okay, so this chart demonstrates on a high level the design flow that we propose today. So you need to create your 3D solid model. You have process parameters, material parameters behind this. And there are two different ways how you can create this. You can use layout data to kind of automatically extract together with the process information a 3D model. This is the way that engineers seems to be preferred. Possibly because it kind of follows the wafer flow in a fab, right? You use layout data to create your structure in a wafer fab. And complementary to this, you can use a library of components, like a Lego system, so beams, plates, shells. And both components actually are now work well together, so in a way they are combined. I show an example later how this would work. But the end is you get a 3D model that has multi-physics behind it, where you can do device simulation on on different levels, but you can also use the same kind of model, use it in a different form, a different view, to simulate it in MATLAB Simulink or in Cadence simulation. And it also goes together with package co-design. So what are now these elements behind this approach of compact modeling? So they are really MEMS dedicated multi-physics elements. There might be other application to this. We focus mainly on the MEMS market. So for example, for the electrostatics, you see here a cross-section of a comp shape. So there are sidewalls are not always straight, right? So they might be tilted. You have fringing effects, which can become even more important than the main capacitance due to the structures. You have electrodes above or beneath that you need to take into account. And one method we used to take this into account is conformal mapping theory. It allows us to be very accurate, detect small changes in capacitance, and it's very fast, right? So this is what we use for the electrostatics, and we combine this with the mechanics. Depending on your structure, you are able to use shapes like beams, Bernoulli or Timoshenko. Different mechanical models are behind this. So if you know that a beam is a beam, you are able basically to gain simulation speed by using specific mechanics theories. If you know that's a shell, you can apply specific shell models to this. So the 10 years ago, the idea was that we can build up a mechanical system only by these building blocks. But what we learned over the last few years is that for certain aspects of your design, the complexity is just at a level, and the need for mechanical accuracy is at a level that you need to use standard finite element approach, hexagonal bricks. So we combine in our mechanical designs now all these methods to get, depending on the complexity of your design, the right level of modeling. So always try to find a model that has the less degrees of freedom to gain simulation speed, but have the possibility to also use meshing capabilities if you need to improve accuracy. Then together with the electrostatics and the mechanics, we also implemented squeeze film damping in these elements based on Reynolds equation, which is, you see here an example of comp drive, which is simply necessary to get the transient simulation right. And then we also have model order reduction, because also, let's say, typically these compact models run 100 times faster, just an order of magnitude, than standard finite element. If you want to combine it into a system with electronics, it can be too slow. So we apply standard reduced order modeling methods to further decrease the number of freedom for the systems to be able to run transient simulations and combine electronics and multiphysics mechanics. So all this is ending up into a design flow, which I call digital qualification, because we really like to go from concept to manufacturing and use this flow. So 3D model entry, which needs to be process sensitive. You can then do device simulation. And thanks to the accuracy and the speed of the models, it allows you to run a lots of experiments. So this is done when you create your design to optimize your design, but also then if you go into manufacturing to evaluate manufacturability and play between design and process. And the next step is then to go over into the system level, where you handle the complete system, MEMS, IC, and packaging. Okay, with this, I go over to show a few case studies to demonstrate basically this design flow. This is quite a simple structure. You see a comp drive accelerometer, SOI based, with comp capacitors for drive and comp capacitors for sense with some suspension. All this is implemented into a sigma delta control circuits. The next slide shows you how to basically build up the system. So there are two ways to do it. Either you can do it from the library of building blocks. So you take the comp shapes, you take the suspension beams, you take the plates. Obviously, that is all parameterizable. And you can also use MATLAB scripting to automate it. That is one way. The other way is that you use a layout. As I said earlier, most engineers prefer to use this method, but then from a layout you need to match now the components, and we do this by applying some pattern recognitions algorithms. So if you draw a comp shape, the software is able to identify this as a comp or as a beam. So, and this allows you to relatively quickly create a 3D model, which is not only a 3D representation, but which has all the multiphysics behind it. So very MEMS specific, but very powerful to create a fully coupled multiphysics models. And once you have done this, it allows you to run standard simulations you would do in MEMS design, static deformation due to stress, modal analysis, frequency analysis. This is one of the most basic but still most important simulations you run, and you need to be very accurate, not only in the first modes but up to 20, 30, 40, even more modes. And which is, mechanically speaking, for complex systems, not always as trivial. And then you have more advanced analysis, pull-in analysis, right? That's how we started here at MIT, coupling mechanics and electrostatics. It's still a problem that can create instabilities, so you need to carefully follow the algorithm to allow a simulation, non-linear aspects of this, frequency hysteresis, and more things like noise. For example, for microphone, noise is a very important parameter, the most important maybe. So once you have done these simulations, you can do also more what we call reliability related or verification analysis. So this is showing an example of still the same accelerometer where you can now apply a shock wave, because the model runs fast. The shock wave is a very complicated simulation, so a transient, non-trivial, and then you have contacts involved, which is one of the hardest problems to solve. But by having fully coupled systems, it allows you to run these shock analysis. It's a typical test used in automotive qualification, the drop test. You let drop your device from 1 meter and it needs to survive. So this is a way how you can virtually anticipate how your device would react and help, also seeing it in 3D, fully understanding what happens, right? Because the electrical signal not always gives you all the clues. So this is a method. This year we published actually an article with NXP, one of the pioneers in this area for automotive sensors, and it's a technology flow that is now used. But then you can now go over from the device to the system level, right? And I don't have a lot of explanation, but basically it's the same model or the order reduced model that you can now visualize in a different view, right? You have it as a MATLAB schematic, or you have it in Cadence as a Cadence schematic, but behind is the same model. So you share the same, well, you can call it golden model, between the mechanical multifix simulation for the device level, or you can use it on system simulation for MATLAB, or for the IC designer in Cadence Simulink, and all goes back to the same model with the same parameters. So I have still time for a few more examples. So this is an example of a 3D gyroscope, like find in all smartphone devices. And here as well, so this is a 3-axis gyroscope. A gyroscope, right, it measures Coriolis force. So you have the 3 axes. So one axis you need to actuate. One axis is the rotation that you want to measure. And on the 3rd axis, perpendicular to those 2, you have the detection of the force that you would like to measure, usually by capacitance, right? So this shows the driving mode here, and then the sense signals according the 3 axes. And you see below graph that shows basically the simulation of the capacitance change if you apply a bias to the electrode. So it's pull in, pull out behavior. So it's a fully coupled simulation, mechanics and electrostatics. Or you can also apply or tune the frequency by applying a voltage, so there's a frequency shift. And this device, right, if it goes into package, it will change behavior because the package deforms. So this is the methodology that shows how we basically do some package simulations over temperature, very basic mechanical, thermomechanical simulations. But the nice thing is you can now feed back this deformation to the device, and you can achieve a nice temperature sweep and see how the device function, the frequency changes, also a transient simulation changes in function of the packaging behavior. One last example is, and this is very simplistic here, but we now work with the best edge engineers in the world to better understand how the edge behavior of crystal silicon, deep reactive ion edge, is affecting the device behavior. And if you look on the requirements for example, that gyroscope or accelerometers need to or buy to be in systems that help to automotive drive your car or other vehicles, the specification of these sidewalls is 0.01 degree. So it's a level that's very difficult to measure physically by SEM. But however, you would see these effects in your device in terms of a quadrature error that's called. It's an error signal that is created by this tilt. So you can use, if you have a predictive model, you can now use this tilt data and feed it into your model. You can also use CD, right? Tilt and CD. There might be also more complicated shapes than only a tilt angle that you can now simulate in your model, make understanding what this quadrature array effect is. So you can play, if you have experimental data, you can map your model to this experimental data, but you also can, for example, anticipate or predict the sidewall angle based on your electrical data. So again, sidewall angles that are physically difficult to measure. With your predictive model and the interaction between sidewall angle and electrical signal, you can understand what the sidewall angle distribution, for example, of the wafer is if you measure an electrical signal. So these are the problems that at the moment keeps us quite busy and helps our customers to move forward. So in the last few minutes, I wanted to give also some example on academic designs. It's stated a bit, but I like to show them because it was a nice contest that we did together with Cadence, one of our partner companies in electronic design, and a foundry, X-FAB in Germany. So X-FAB developed a technology that allows inertial sensor, basically SOI technology that allows to fabricate inertial sensors. And the idea of the contest was to see what else we can do. It was open to everybody, but mostly universities participated. Can we have other ideas that can use this technology? So people could either use just the MEMS design, could only work on the electronic design because it's a combined technology where you can have MEMS and electronics, or in best case use both, right? Do a MEMS design and develop the electronics and put it together. And I just show you a few of the outcomes. We had, I think, about 20 projects submitted at that time, and one of them, this one was focusing more on the MEMS side. So it's using a genetic algorithm that allows you to optimize your structure. In this case, it's an accelerometer with a specific preamplifier motion. And it uses a genetic algorithm, right? Something that is not standard used in industry, certainly not. But having a fully parameterized model and running it at MATLAB allows this genetic algorithm to find optimized form to a specific problem. Manufacturability is a different question here, but again, it allows you to find some unexpected geometries that you might not have found otherwise. Another example is this. It's a very simple structure, a clamp beam. In this case, the idea is to use it as a part of a programmable logic device. In this case, a simple mechanical structure, but well implemented together with the electronics to have a full microelectromechanical systems co-simulated in his electrical environment. And a third example, so this is now a more complex mechanical geometry. It's an energy harvester, right? And instead of applying a voltage to actuate the device, you use the vibration sense to basically create a voltage that can be read out, in this case a Bennett circuit. And again, it was a nice work because it was combining integrated design approach together with electronics and MEMS. So with this, I would like to conclude. So I hope it was not a very scientific talk, right? So my background is MEMS design, it's not modeling. If you have more questions, my colleague Matt Cameron is really one of our, what I would call head and scientists. And also Steve Centuri volunteered to talk a little bit about the history. So that's very nice of you, and I'm looking forward to also learn about this. Before this, just like to conclude. So over the last years, we contributed to help our customers to tackle problems in multiphysics, applying reduced order models, looking now more and more on manufacturability aspects, right? The development time of MEMS continues to be still high compared to IC, so we believe we can help with combining the know-how from manufacturing with our design capabilities. And reliability will be always a issue where there are lots of research projects, so we don't think we can handle this by our own. So we work, first of all, with our customers, with EDA partners together, but also we are always open to collaborate with academia and research on new topics and new devices and especially new methods. With this I conclude, and I'd like to thank you very much for your attention.
Yeah, will this work? That's okay?
Can I give you this one real quick?
Would you put your early slide with the growth of MEMS up? I think it was your second slide or something. Way back.
Yeah, the first.
Because you started 1990. Keep going there. That one. Yeah. Whoop. Next slide. That's it. You have it starting in 1990, but actually there was already a market for MEMS in 1990. It was mostly pressure sensors, blood pressure sensors, small sensors, almost entirely diaphragm etched. And this was a time in 1990 when there was enough interest in MEMS for a lot of people to be looking for new kinds of devices to make. And accelerometers, switches, mirrors were all on the agenda at that time. Now, it's 2022 now, and I'm going to go back 35 years to 1987 in Tokyo at Transducers 1987, where I made an invited talk, and the slide that you showed from my book was basically in that talk. The design, process, system, materials were there as a proposal for how to accelerate the development of MEMS devices by creating integrated designs. That was in 1987. It took a little while to get some funding, but I finally got some, and I had a group and a partnership. It was an MTL RLE partnership. I was the MTL person, and Jacob White was the RLE person. Jacob White had developed with his students the FastCap program for high-speed simulation of capacitance. And the reason that's a difficult problem is that it's external to the electrodes. So if you try to do it with finite elements, you have to fill all of space. Whereas if you can do a surface-based calculation, it's much faster. Matt Kaman later did his work on Fast Henry, which was an inductance simulator based on a similar approach of trying to use the physical structure rather than the external space as the basis for a simulation. My interest was in generating the 3D dimensions of the 3D model from the process flow. And that's what we worked on. And together we created a system which we called MEMCAD. The glue, the person who put it all together was John Gilbert, a postdoc in my group, and he, with Mike Jamolkowski, became the co-founders of Coventer in 1995, 1996, and they actually licensed from MIT not only the initial software, FastCap and some of the other components that we had developed for generating 3D models from process flows. That was a very significant thing. They could take those 3D models, put them into a finite element program, and calculate how the device would perform. And this was a big deal then. The initial name of the company was Microcosm Technologies, and I wore my Microcosm shirt. I was not a co-founder of the company because I had money from DARPA at that time, and I decided that I could not start a company while I was also supported by DARPA. So I watched with interest, and when my DARPA funding ended and I was invited to join the technical advisory board for what was then Microcosm Technologies, later renamed Coventer, MEMCAD later became Coventerware, And the thing that's interesting is you think about startup companies, you usually think of an exit in 10 years, 5 years, that kind of thing. Coventor was a 20-year exit for the founders. It was founded in 1996, was sold to Lam in 2017. That's a 20-year stretch. And the thing that I want to impress on you is the long time scale necessary to go from conception to the kind of true sophistication that's now captured in the Coventor tools. For example, manufacturability, which in our early work we couldn't touch. But now, with enough cumulative wisdom and knowledge and experience and focus, you can get to the point where you can solve these very important issues that enable products at a much better rate. But the development time is still long. It really is a fact. And finding a process and a structure and a package and a system that all go together is still an enormous challenge. Read my book.
Very impressive history. So now the talk is open to questions. Any questions? So maybe I can start with one. So you show that in 2018 there was a contest for using the Coventor and also Candice software for MEMS design. So is this is there future plans to hold that kind of contest again? Or?
I would pretty much like so personally, but actually it was a lot of work, and we a company, right? So if there is a consortium of partners working together, we are very happy to support this, because I think it was a great idea to basically use standard technology in terms of simulation and in terms of hardware, and to come up with new ideas. But it requires a certain sophistication of organization, right? So we're happy to support and help, but only with strong partners.
Yeah, thanks. Other question? Yeah, Tai.
As you said, packaging is always an issue that you have to consider along with the device. But lately, one of the things that has been coming up is that life has become more interesting in terms of heterogeneously integrating different technologies together with the package. And what kind of challenges do you see these, how these evolves over time, given the platform that you have, which has already tackled some of the problems, but is extending it?
Yeah, right. I probably need to be humble and tell you that, I mean, there are lots of aspects which is probably out of my career or my competence area. So it's clear we focus on on the traditional MEMS market. What we see there is that although the packaging becomes more and more sophisticated, so you have not only the device that is micro machined, but the package is getting now more and more micro machined. So you can. There are providers of wafers or packages that, it's half of the MEMS device with cavities and other functionalities. So this is something that is more structural that can be included. But then you have a range of other physics, which I have not mentioned. It's the optics, right? There's a new world of optics coming now with waveguides implemented, and that require certain specific technologies. It's not of the roadmap for Coventor MP. It's a roadmap for other products we serve. Not sure if I really answered your question, but I think we are still busy enough with the conventional MEMS stuff and packaging, pressure sensors, mirrors they need, right? You need to shine light into it. That keeps us busy, so we even not look far ahead of all the other challenges that are out there.
Thanks. Any other question? Yes.
So one of the things you'd mentioned is that there is a life expectancy to some of these kinds of devices. So for example, let's say, an accelerometer that you can buy off the market, like an ADXL345, one of the things that you see is that they do talk about calibrating it when you first get it. But there's actually nothing that I've seen in the data sheets that says that, well, expect it to fail after 2 years or 3 years or 4 years. There's nothing like that. So I'm wondering if that's something that we should be aware of when we take a package like that and we integrate it into a board, an actual device that you can buy off the market on DigiKey or something like that.
Yeah, what can I say? So, I when I started out in industry before joining Quenta, I was designing accelerometers for airbag crash sensors, a small company, Sensor, very simple structures. And I follow this. So the MEMS part is very reliable, and especially if it's crystal silicon. The lifetime is almost not an issue, right? There, of course, you need to take into account shocks, but if it's well designed, they are almost very few failure modes, right? What is then the electronics around it, and maybe how pads and this is connected. So this is where the real reliability problem comes in terms of lifetime. So this is, I would say, for the crystal silicon type of devices, where lifetime is just very long. But then you have obviously another area of actuators, switches, right, which might be not crystal silicon, metals, and their lifetime is an issue and wear. And some of things you can predict. Many of things you need, it's very difficult to predict. So this is, I think, the challenge of each MEMS company, right? The customer comes and asks this question, so how long can I use your device? It's, I don't need to answer this, so I don't have a perfect answer, but I think it's a non-trivial answer to do. But history shows that MEMS can be extremely reliable.
Could there be some sort of a flag that comes up saying, trying to replace this device?
Well, I know we are looking into this many years ago and couldn't find up with a really good way to simulate and model this. But this was the idea to have a predicted lifetime, to have a flag or some time. So what I think you have a lot of now work going on in machine learning algorithms. I think this is, and I know also actually some of our customers they work on this, right? So this is probably the way to go forward, to find machine learning algorithms that can help you to answer this question.
Thanks. Other question? Yeah.
So there's a lot of new materials entering like the semiconductor and MEMS space and everything beyond just silicon. How well do the models that you guys developed kind of extrapolate to these new material systems, or how accurate can you model them if you're working on some obscure quaternary alloy or something like that? Is it able to account for different mechanical properties?
So, right. So what we don't predict any material properties. And so what we do have, we have a database where the user need to put in these material properties. For some materials that are well known, right, we have a standard values that can be applied. But for other new materials, you basically need to measure them. So what we can do, we can advise companies how to, for example, characterize a Young modulus. But that is the way that needs to be happen, and this is important, because if you don't know your material properties, you can't predict your device behavior. So, and one material or one family of material we now look more actively on is piezoelectrics, because this is becoming more and more popular. So there we have some more data in house, but at the end it remains also at the charge of the user to qualify his material properties.
But you can't adjust them then?
Yes, right. And this is very important, right? That you need to adjust them.
Thank you.
Okay, great. So let's thank our speaker again for this wonderful
Thank you.
talk.